day everyone, welcome to Sir Phax Learning Channel. For today's video, pag-aaralan po natin ay ang Rotational Kinematics. Ano nga ba ang Rotational Kinematics? Kung gusto mong malaman, panoorin mo ang video ito. Ang pag-uusapan niya natin ngayon ay patungkol po sa rotational kinematics. This is another video lesson for second quarter, week 1 for General Physics 1 about rotational dynamics or the rotational kinematics. Rotational motion. The general motion of a rigid object will include both rotational and translational components. So, for example, the motion of a wheel on a moving bicycle, a wobbling football in flight is more complex case. So, when we say rotation, it's either rotation with only one fixed point or rotation with fixed axis. So, yun po yung dalawang rotation. Probably tumutukoy pag sinabi po nating rotation. It's either mayroon siyang fixed point or mayroon siyang fixed axis. So, but for pure rotation, we talk about the rotational with fixed axis. So, may dalawang definitions yung pure rotation. Every point, the first one is every point of the body moves in a circular path. So every point of a body moves in a circular path. Tama naman. The center of this circle, so this is the center. Dalawa. So the center of this circle must lie on a common straight line, which is called the axis of rotation. So this is the axis of rotation. Any reference, the second definition of pure rotation is any reference line perpendicular to the axis, such as A to B. In this figure, moves through the same angle in a given time interval. Now, how many freedoms are needed to describe completely for a pure rotation? So probably mayroon kang isang revolution needed to complete a pure revolution. Now, how many for a rotation with only one fixed point? Kung isa lang yung fixed point, ilang freedoms meron? So you need 3 revolution. Take note for this, ha? If you want to describe a pure rotation, you need 1 revolution. If we will talk about fixed point, it needs 3 revolution. In general, the 3-dimensional description of a rigid body requires 6 coordinates. Take note for the coordinates. 3 to locate the center of mass, 2 angles such as latitude and longitude to orient the axis of rotation, and 1 angle to describe rotations about the axis. Let's talk about the rotational variables. So for rotational variables, the first thing here is the angular displacement. In this figure 8-4, it shows a rod. It shows a rod rotating about the z-axis. Where is the z-axis here? So this is the z-axis. Any point P on the rod will trace an arc of a circle. So any point P on this rod will trace, this is the rod, z-axis. Any point P will trace on arc of a circle. The angle theta is the angle theta. So we get this up to here. The angle theta is the angular position of the reference line AP. So this is our reference line AP. Reference line AP2, AP1 is the reference line AP with respect to the x-axis. So this is AP with respect to x-axis. We choose the positive sense, the rotation, sense of the rotation to be counterclockwise. So take note, if the movement in a rotation, if the movement is clockwise, your torque is negative, but if clockwise, positive. So we choose the positive sense, the rotation to be counterclockwise. So therefore, your theta here is equals to S over R, or arc length over the radius. Okay? Where S is the arc which the point P moves, and R is the radius AP. So kung babalikan po natin, ito. Okay? And at time T, the angular position is theta sub 1. And at T sub 2 is equal to theta sub 2. So theta sub 1 at T sub 2, theta sub 2. At T sub 1, theta sub 1, this is your angle 1. At T sub 2, or period 2, is theta sub 2. Okay? During the change of time, or delta T, that is equal to T sub 2 minus T sub 1. The second thing is the angular velocity. To define angular velocity, we define it as the average angular velocity, or omega average velocity is equals to the change of theta, or change of angle, over the change of time, or delta T. The instantaneous angular velocity omega is equal to the limit of delta T to 0 times the delta theta over the delta T, or displacement times each theta over the displacement times time. Now, in this case, is omega a vector quantity? What do you think? Write down your answer on the description box, or comment box rather. So the dimensions of omega inverse time, its units may be radians per second or revolutions per second. And therefore, what do you think? Is our omega here a vector quantity, since each units may be radians per second or revolutions per second? Comment down your ideas on the comment section. The third one is the angular acceleration. Speaking of angular acceleration, if the angular velocity of P is constant, then the average angular acceleration is defined as alpha average velocity is equal to the change of your omega over the change of time. Therefore, the instantaneous angular acceleration is alpha is equal to the limit of delta t towards 0 or times delta omega over delta time, which is equal to the displacement of omega and the displacement of time. Or derivative of omega or derivative of time over derivative of time. Its dimension are inverse time squared, and its units might be radiation per second squared or revolutions per second squared. Now, since we are talking about rotational kinematics, rotational quantities as vectors. Let's talk about rotational quantities as vectors. Commutative addition law for any vectors, vector A plus vector B is equal to vector B plus vector A. Can an angular displacement satisfy corresponding formula in which delta theta sub 1 plus delta theta sub 2 is equal to delta theta sub 2 plus delta theta sub 1. So, pwede ba nating iparehas to dito sa vector A plus vector B is equals to vector B plus vector A? Tingnan po natin as we go along with our discussion. As an example, we first rotate a book. So, let's say there is a book at delta theta 1. You rotate it at 90 degrees about x-axis, followed by delta theta 2 at 90 degrees as well, or by about z-axis. But if we first rotate the book at delta theta 2, which is 90 degrees, by about z-axis, and the delta theta 1 at 90 degrees by about x-axis, probably the final positions of the book are different. We conclude that delta theta 1 plus delta theta 2 is not equal to delta theta 2 plus delta theta 1. And so, finite angular displacement cannot be represented as vector quantities. So, angular displacement are not vector quantities. If the angular displacement are made infinitesimal, the order of the rotations no longer affect the final outcome. And that is derivative of theta 1 plus the derivative of theta 2 is equals to the derivative of theta 2 plus the derivative of theta 1. Hence, the derivative of theta can be represented as vectors. Quantities defined in terms of infinitesimal angular displacement may also be vectors. For example, you have angular or you have omega is a vector. So you have here vector omega is equal to the derivative of the vector theta over the derivative of time. So this is not displacement but derivative. Its direction is determined by a right-handed system shown here. Right-handed system, right-hand rule. The angular acceleration, same true with the angular acceleration, vector alpha is equals to the derivative of vector omega over the derivative of time. Is also a vector quantity. So, nagiging vector quantities itong ating angular displacement once na naging infinitesimal itong ating angular displacement. For the rotational motion of a particle or a rigid body around a fixed axis, which we take to be z-axis. The simplest type of motion is that in which the angular acceleration is equal to 0. Take note for this, the simplest type of motion is that in which the angular acceleration is equal to 0 for fixed axis. The next simplest motion is alpha is equal to a constant, or the derivative of your omega is equal to alpha, which is also equal to the derivative of time. We now integrate on the left from omega sub 0, which is equal to omega, and on the right from time 0 to time t sub 1. So shown it here. The integration of omega to omega sub 0 times the derivative of the omega, which is equal to the integral of t to 0 times its alpha, which is equal to the derivative of time, which is also equal to the alpha to t, the integral of t to 0 derivative of time, and so on and so forth as shown here. Therefore, we obtain omega z is equals to omega 0z plus, or sub 0 to z, plus alpha sub z times time. And the derivative of theta over the derivative of time is equal to omega z sub z. And the derivative of your theta is equals to omega sub z, derivative of time. And then integrate the equation again, as shown here. Therefore, you have theta is equals to the theta sub 0 plus omega 0 to z, or sub 0 to z, times time, plus alpha sub z to the square times the square of time over 2, which is similar to the equation x is equals to x sub 0 plus v sub 0 to x times time plus a sub x times t squared over 2. So what are the relationship between linear and angular variables? When a rigid body rotates about a fixed axis, we have arc length is equal to theta times the radius, where is the distance which the particle moves along the arc, and the radius r is the perpendicular distance from the particle to the axis, and the theta is the angle which the rigid body rotates through. So as shown here, s is the distance which the particle moves, so this is our s. R is the radius, and theta is the angle. So differentiating both sides with respect to the time, note here that the time that r is constant, we obtain the derivative of s over the derivative of time is equal to the derivative of theta over the derivative of time times r. So velocity sub t, or v sub t, is equals to your angle omega times r, where derivative of s over derivative of time is equal to total velocity, which is the tangential linear speed of your total velocity. So the speed is equal to the derivative of s over the derivative of time, which is equal to the derivative, the component of the derivative of your radius over derivative of time is equal to your component of your speed or velocity. So by differentiation, you get alpha sub t is equals to alpha times its radius, where derivative of your velocity, total velocity over derivative of time is equals to your total acceleration, which is the magnitude of the tangential component of the acceleration. And the radial or centripetal acceleration is equal to the square of velocity times time over the radius. In angular displacement, that is omega squared times r. Now, for rotational with fixed axis, we have the arc is equals to theta r. The total velocity is omega times r. The total acceleration is alpha sub 2 times the radius, and that is equal to a sub r is equals to the total velocity squared over r, which is equal to omega squared times r. So notate them in vector style. So ito po yung vector style niya. The vector v is equals to vector omega times the vector r. And the vector a is equals to the vector alpha times x times the r vector plus omega vector plus v vector, as represented here on the figure. All right.